So let's take a look at this next slide where I relate these parameters. So if we were to take the concept of force, the thing that's generating motion, if we're talking about a hydraulic system, we use the term pressure. The units for pressure might be PSI, might be bar, we might use water column. It's all the same thing describing a force that's distributed across the water. Electrically speaking, we use the term voltage. The units for volts are volts. Again, voltage is just like pressure in water systems. If we were to talk about flow, how much of something is moving, we use flow rate in water systems. That could be gallons per minute, liters per hour. And in electrical systems, we describe the current. The units for current are amperes, or more simply, amps. Now, these next two slides are the most important slides to remember. Remember that when we're talking about electricity and you hear the word volts, that's just the electrical word for pressure. Voltage is the force or the pressure that's acting on these electrons that generates the flow, that generates the current to be moving through the wire. That's generating these electrons to move. And when we talk about flow, current, electrical current, current is what happens due to the force, due to the pressure, the voltage. All right, so current is the resulting number or rate of electrons flowing through a cross-sectional area of the wire. In addition to those two parameters, we also need to bring up resistance. Hydraulically speaking, that's going to be your friction factor, your head loss on a pipe. How much resistance to flow is there? In electrical systems, we call that ohms. It's a strange word. We use the Greek symbol omega to represent that. But electrical resistance is what slows down the flow of electricity. Examples of electrical resistance could be a really long stretch of electrical wire. That's going to have resistance. That's going to make it more difficult to push those electrons through. Other examples could be a light bulb, you might call it a resistor, a pump. All of those are examples of resistance. These three parameters, I think, are best described using this photo here. This describes its relationship. There's a law called Ohm's law, which is simply the voltage is going to be equal to the multiplication of your current and your resistance. Now, if we look at this photo, it's kind of funny photo, but we have the volts which are pushing the amps through the wire. But those amps don't get to just go freely and easily. The ohms are resisting, they're restricting the flow of amps, okay? And then if we remember this relationship up here, it's a very simple relationship. If I were to leave voltage the same, double my resistance, I'm only going to get half the amount of amps through my system. If I were to double my volts and leave the ohms the same, I'll get twice the number of amps through the system. So just remember, it takes 1 volt to push 1 amp through 1 ohm. Now let's get a little bit more practical here and talk about different circuit geometries or configurations that we're going to run into. There are 2 fundamental circuit configurations. One is series, and the other is parallel. Now, these symbols right here, these zigzagged lines, that's the symbol for a resistor. So instead of thinking of some obscure zigzag line, just imagine there's a light bulb. in that place, okay? And that light bulb is shining out light. So these are just 3 different light bulbs, all shining out light. All right, so if we're going to talk about the definition of a circuit that's in series, imagine that we have an electron that's being pushed by this battery. The symbol right here is the symbol for a battery, which is creating electric pressure, voltage. And that electron is coming out of our battery. It's following our wire. It has to go through this light bulb, this resistor, through this one, then it's going to come back around and get re-energized, repressurized, and it's just going to do that. It's got no different paths that it could possibly take. There's just one branch of this circuit. If we were to go over to the parallel circuits, and we have this electron that comes out of our battery, comes over here, it's going to reach a point where there is a branch. There is different paths that it could take. It could take this path through that resistor, that light bulb, and back to the battery. Or it could also take the different path and then come through this light bulb and back to the battery. Or perhaps it could go through that light bulb and back to the battery. When you have a parallel circuit, you have multiple path options, different branches that this electron could go through. When you have a series circuit, there is only one option for the flow of electricity. So to bring this back, these are drawn some solar modules. Are these solar modules wired in series or parallel? Let's look at this. Now you'll see here down at the bottom, I'm using the term load. That is a generic term. It could be a light bulb, it could be a pump. A load is, what is it that you're powering, okay? So a load is anything that we're delivering power to. So let's think about an electron in this situation. So we've got an electron that is kicked out of this solar panel. It's going to follow this wire, follow the wire, come around, turn the pump, turn on the light bulb, something like that. It's going to keep coming around, keep coming around. It's going to go through this solar panel, and come through this solar panel, and throughout that whole path, that complete circuit, there was no branching. There was no alternative paths that it could have taken. That means that this arrangement of solar panels is series. So what is this? We have 4 solar panels again, but it's wired differently. Again, we have a load, which could be a pump, it could be a light bulb, it could be anything you want, a water heater. But these solar panels are wired differently. So let's follow the path. I come through here, we go towards my load, I come over, and I come back here, and I have an option. I have multiple paths that we could take. I could return this way and come back, but it could also come over here through the solar panel and back down and around. Or the next time, it could come up here. There's multiple path options that are available to the flow of electricity. So this means that this solar panel arrangement is in parallel.